So our next speaker is Tom de Jong, and he will talk about relating ordinals and set theory to ordinals and type theory.
Yes, thanks. Right, so I could say first that this is a joint work with Frederick Nordfeld Forsberg and Chongji Xu and our esteemed chair about the ordinals in set theory and ordinals in type theory. And so we're going to relate these two. I'll sketch out the two approaches, and then we'll relate them in homotopy type theory. So that's going to be my base theory. So first, let's do a little bit of recap on ordinals in set theory. So one possible definition of doing this is as hereditarily transitive sets. So a set X is transitive if for every element of that set, and then you take an element of that element again, then that third element was already in the original set, right? So you can sort of go two levels deep, and then you can go back again. And then a set theoretic ordinal is a transitive set whose elements are all transitive. And then you can actually show that this sort of goes all the way down. So it's not just that the elements are themselves transitive, but those elements of elements are again transitive. So it's hereditarily transitive. So here's a few examples. So empty set, singleton empty set. The set where you have the empty set and the singleton empty set are all set theoretic ordinals. But this one is not, because you have this non-transitive setting there. And you can imagine how you might build them up, right, from these things using the axioms of set theory. Okay, so one thing to notice here that this is sort of inherently making use of the global set membership relation, right? Like having a y and an x, and then I'm reusing that, the z and the y, and so on. So in type theory, you know, if you might just sort of call them, you do things differently. One approach to ordinals, as set out in the homotopy type theory book, is to have types equipped with a binary proposition valued relation that is transitive, extensional, and well-founded. So the type X here, we have a relation. So transitivity is the usual thing, and extensionality means that that two elements are identified exactly when they have the same predecessors, right? So for every u in X is used below X, then it's that happens exactly when u is below Y, and then of course one direction is immediate, right? And the other one is really the extensionality axiom. And it follows actually that then X is an H set, because this relation is proposition valued. So yeah, you can do a little proof there. Right, and the other thing is well-foundedness. So strictly speaking, well-foundedness is defined in terms of acceptability. But it's helpful to think of these sort of equivalent assertion that whenever you have a family of types over X, you can think of this as a property, then you can prove that the property holds everywhere if you can prove it assuming that it holds for all of the predecessors, right? So assuming you have P of Y for every Y below X. And so these are the axioms, and then you get these type theoretic ordinals. Okay. So then, of course, once we have that, we collect them all up into a type. So we write type for the type of small, let's say for some fixed universe, type theoretic ordinals. And the next thing I would like to do, because I would like to relate the two approaches, is I would like to have the set theoretic ordinals inside POP. Luckily, in another chapter of the HoTT, there's this model V, so called the commutative hierarchy there, and it's a model of some constructive set theory. And one way to actually get this V is as a hit. There's an alternative approach to hit root using a normal W type, and then you take it as a subtype. I'm sure we'll hear about that in next talk. Yes, good morning. Wonderful. So I'll do this one, and you get to see the other one next talk. So you have a point constructor V set, which for every A in some universe U, and like a function going from A into V, and you quotient it by bisimilarity. So two of those guys are going to be the same when F and G have the same image. So the idea of V is that this is going to give you the elements of your set, and A is just like a labeling type, right? You the labels for all your elements in the set. And then you define set membership as a predicate on V. So you say that X is in some V set AF exactly when there exists an A, such that F of A equals X. Okay. And now, because the definitions of a set theoretic ordinal, this hereditarily transitive notion, all you need for that is you need a set membership. So you just take this, and in type theory, you then write down a subtype V ord of the set theoretic ordinals inside V. Okay, so that's all the structure you need in order to write that down. So that's what we do. And now we have V ord, and we have ordered. So it's a type of type theoretic ordinals, and we have a type of set theoretic ordinals. And of course, the fun is that these things are equivalent. So let's see how they are equivalent. So you define maps back and forth, of course. So the first map is capital Pi here. So it goes from type theoretic ordinals to set theoretic ordinals. And this is done by transfinite recursion. So you take an ordinal alpha, and then you send it to this V set indexed by the ordinal itself. And then for every point in there, you have to give something in V. But by induction, you can apply the phi to smaller ordinals already. And this is a smaller ordinal because this is exactly like an initial segment of alpha determined by this point. Right? So these are all the points in alpha that are below this given point A here. And so by this principle of transfinite recursion, we can apply it to all those smaller ordinals, and this is actually well defined. You get the transfinite recursion from the well-foundedness in the definition of the type theoretic ordinal. And it's actually quite I mean, it looks maybe a little bit complicated, but it's quite convenient because you can now prove things about this function using transfinite induction, right? You define something using recursion, so you prove things using induction. So that's quite nice. And then you define the inverse, and actually the inverse is quite a familiar function. If you open a book on set theory, you'll see this as the rank. So you take a V set AF, and now you send it to the supremum or the join of ordinals. So because this thing was like it's a subtype of a HoTT, it's an inductive thing. So we can assume that we already have, that we can apply this psi on like this on these f of a's here. And now you just kind of bunch them up, and you just have to add the +1 to make things work. It's kind of like taking a set and then wrapping one more curly brackets around them into this singleton type, and then you wrap them all up, and it works well. And again, it's a recursive thing which allows you to prove things by induction. But it's also possible to give maybe conceptually simpler descriptions of these functions. For example, one description is that psi of something x in V is the type of elements of X, right? So it's kind of simple. It's just that this is up to psi, so be a bit careful. Another description is where you take psi of a V set AF, and actually because we restrict to set theoretic ordinals, which are, remember, hereditarily translated, all of the information of such a thing is already at the top level. Because the elements, you can always like sort of drag them back up to the top level, which is why you can get away with just taking some quotient of A here. You don't need sort of the full structure of F. Although you do, then you have to identify A and B since images are equal. Anyway, just to show that you can have these non-descriptive versions. Anyway, non-recursive descriptions. So these are the two maps. But then that's not quite the full story, because we do get, okay, the types are equivalent. That's kind of nice, but actually you can do a bit better, because the type of type theoretic ordinals is actually type theoretic ordinal itself, where you say that one ordinal is below another if the first one is an initial segment of the second, which just means that you have a point in beta such that alpha is this initial segment of beta. Okay, and the y is unique, so we don't need something like a truncated sigma here. And then on the other side, you have V ord, and actually you can prove that set membership makes V ord into a large type theoretic ordinal itself, right? So this is a transitive relation by definition, really, and it's well founded and extensional because the model of like this cumulative hierarchy in HoTT models the corresponding axioms of set theory. So the extensionality axiom and the axiom of set membership induction. Because of those things, you get that this is a type theoretic ordinal. And then the maps that I sketched on the previous slide are actually isomorphisms of type theoretic ordinals. So this thing kind of transfers to this statement here that when you look at the set theoretic ordinals with the set membership relation and the type theoretic ordinals with this initial segment relation, then these two structures are isomorphic. So you might sort of put that in a little slogan and say that set theoretic and type theoretic ordinals they coincide. So that's roughly the first half of the story, which is good. Exactly halfway. So this is the big picture, and so where are we going to go next? Well, we're going to go to the bigger picture. which is where we draw this little square here. So we now know that the set theoretic ordinals, this V ord here, is equivalent to the type theoretic ordinals ord, and this was a subtype of V. And so then it's quite natural to ask what sort of fits in the square here. Now, of course, you could cheat, right? You could just take question mark to be V, and then I mean, that's kind of the trivial answer. So it's natural to ask, hey, what kind of ordered structure can we put here? Because this really is a type of ordered structures, right? Whereas this is some HIT or an inductive type. This is a type of order structure. So can you find a type of order structure making this diagram commute? And so then an initial attempt at this might be to simply drop transitivity, because I mean, here you have transitivity, here you have hereditary transitive sets, right? You drop that. So why don't we just drop it here and we just look at the type of extensional well-founded orders? It turns out that doesn't quite work, but you can patch it up to make it work. So that's what these two concepts of the marking and the covering marking are all about. So the starting point will still be an extensional well-founded orders with type with this relation that has these axioms. But now you have a mark, and the marking just sort of intuitively picks out the top level elements of a set. So here's an example illustrating it. So let's say you have these two sets. In some sense, they have the same elements in that this set has the empty set as an element and the singleton empty set as an element. But this one actually also does just like one more level down, right? I mean, you have the singleton empty set, and then that has another element in the empty set. So they're both represented by the two element type, the 0 less than 1. But for this one, we actually mark both of these things because they both sort of are at the top level. Whereas for the second one, you only mark the top level. I mean, this guy is sitting in there. So this guy points to 0, this one points to 1. You only mark this one because it's only there at the top level. This idea of the marking is just giving you it's just telling you which ones are at the top level and which ones are sort of all the way down as a set of an element and so on. And then you need one condition, namely the marking is covering, which means that any element can be reached from a marked top level element. So in some sense, there's no jump in there. Now this idea, as Rich stressed, is not new at all. I mean, this idea of encoding sets as well-founded structures is very old. In particular, there's quite a bit of work in category theory between Osius and Taylor and Adamakino. But this above approach actually worked quite well for us, as we'll explain, for generalizing this theory of orders. Okay, so then we fill the bigger picture. So we write Mivo for this type of covered marked extensional well-founded order. So this spells Mivo. And then you can equip every ordinal with a trivial covering by just simply marking everything. Right? So you take an ordinal, you forget that it was actually transitive, you remember that it is well-founded, you remember that it is extensional, and you just mark everything inside. And that makes ord a subtype of this covered Mivos here. And then all you have to do really is you have to generalize the maps that we did here. You have to generalize the constructions from ordinals to Mivos. So what I mean by that is if I just go back a few slides. So these maps here, like you need a notion of like you have addition of ordinals. So you need a sort of a notion of addition of sets, if you like, and you're just going to take singletons, and you need a notion of supremum is going to be union. Right? So you just need to generalize this a little bit. You need a little bit careful because transitivity doesn't hold. So sometimes the intuitions are a bit thrown off. But that's really the gist of it. And then you get this isomorphism of covered marked extensional well-founded order. So this guy is again, you sort of play the same structure where this was actually an ordinal itself. This becomes a covered Mivo. This one is a covered Mivo, and then you get isomorphism of such structures, making the diagram commute. So I'll wrap up with some time for questions. So the first sort of summary view was that the set theoretic ordinals in this cumulative hierarchy, they coincide with the type theoretic ordinals in HoTT. And if you generalize from the type theoretic ordinals to these so-called covered marked extensional well-founded orders, then you can capture all of the things in the cumulative hierarchy. So you don't need some sort of inductive type, or I mean, this really is already in there as a type of order structures inside HoTT. And there's some questions maybe to think about. So one question, it's quite natural, would be to sort of flip this story on its head, and rather than sort of picking homotopy type theory as the host theory, you pick set theory as the host theory, and then you build a model of HoTT inside of that, and then you ask the same sort of question about set theoretic and type theoretic ordinals. Another one is maybe whether we can use this to sort of pin down this constructive set theory that V models. So can we show, for example, that strong collection is independent? So finally, I would just like to point to the paper, which I'm happy to report was accepted for presentation at LIX, and the corresponding AGDA formalization. Everything I said was formalized in AGDA modulo typos potentially present in this slide. So thank you.
Great. Now we have some time for questions. Alex, please.
So the equivalence between the two types of ordinals, it seemed like that was quite relying on transfer recursion in both directions. This is incorrect. And well, it seemed like it quite heavily relied on the transitive structures like do the recursion. So how does that generalize to the full set? Maybe I just missed something.
Well,
to define the match, you use transfer recursion.
Yes.
So,
but you have that by well-foundedness. It doesn't really, like transitivity doesn't really feature into that.
Right. So okay. So you can still do the construction because you're working with sort of well-founded.
Yes. Yeah. Because you have well-founded structure there.
Okay.
It's just telling you that at some point this will end, but in a more constructive way.
Okay. Any further questions? Yeah.
So, sometimes we say kind of loosely that universes in that theory correspond to like ordinals, and now you have these ordinals. Can you like give something to say about ordinals in your
Yeah, I don't know yet, but it's definitely something that I would like to find out. Also, Ulrich asked something along those lines at some point, but I haven't really sat down to think about it too much. But yes, I would love to think about it.
Okay, and I believe there was another question. Okay. So, any further questions? No, if not, so let's thank Tom again.